My idea for this talk is indeed that I want to not so much focus on the details of physics, Feynman integrals, or whatever there, or on the mathematics on the side. What we will see there is period integrals, paramodular forms. But what I want to do is really highlight this transition between observation in like some discipline, for example physics, in this case astronomy, and then we want to go to the physical modeling. We won't do that in detail. We are not physicists. Well, most of us are not physicists. Some of us are physicists. But then we will go to the mathematical framework. And finally, we want to go to a concrete mathematical contribution. And the idea here is really that I want to once sketch out this line of thinking where, as mathematicians, often we just do our theories in more or less our theoretical vacuum. But in the end, a lot of what we do, historically definitely, but also contemporarily, can and should probably be justified by what's happening in other disciplines, and this is an example of how you could do that. So I want to start the talk by asking you to turn your heads for 30 seconds and look at this. This is a nice picture, or video in fact, that you will see here. And you see some, in fact, two black holes. That's the black holes there. And then around that, a lot of stars. And what you observe there, so this would be the image seen by an observer, this image is distorted by eventually the gravity of those black holes. Exactly 29 seconds, so we're good now. So the black holes are merged, we can start. So what did we see here? This is a simulation, it's from SXS, so space-time, simulation of extreme space-time. This is just some program that physicists use to model the observations by LIGO. So LIGO is an observatory laser interferometer, an observatory for gravitation, And what it enables us to do is to see directly the effect of gravity on, for example, celestial bodies. So the first observation was September 14th. And this was 2015, right? Yes, 2015 was the first observation. Not exactly this one, but another one also of a black hole merger. And this really created a new era of physics. So what we have here is now what you call multi-sensor or multi-detector astronomy. And the idea is that before, of course, we could see radio telescopes, light telescopes, so we had all this visible light, which is useful information, and of course that had already been combined. This is an important tool in astronomy. But now we were, in addition, able to also combine directly the observation of gravitation. And apart from the fact that this is an amazing achievement of experimental physics, this kind of new physics then sparked a lot of new funding, and of course the desire to further understand what has already been observed. And then, this will be the topic for us today, the desire to already lay the groundwork for the next generation. Because what we are seeing here, we can actually quickly go one more 10-second head turn. We can go there to this other picture here. This picture, that's from the ALMA collaboration, and what we see here is a depiction of the universe, or its age rather. So we are here on the right-hand side. At the left-hand side is the Big Bang, which is like the Big Bang theory is the predominant theory for how the universe was created or came to be. And then we see here on a logarithmic time scale certain galaxies forming, clusters, and so on. But here, this is the time until which LIGO can observe things. So we can see some galaxies forming and so on. This is extremely important observation in data. The next generation telescopes, and I will talk about this quickly in a second, but the Einstein telescope is one of those, would look into here, the dark age, which is, for those who know physicists, this is directly after the recombination. So we already have particles in the universe, but they essentially form a plasma, so that light cannot really penetrate the universe, and that means that observational data from electromagnetics cannot really tell us much about that apart from background radiation. So gravitational data that can go into that time has particular and extreme high value, and that's why this next generation of gravitational observatories would be particularly useful. This will be an important point for us, because if we ground our mathematical work in physics and in this observational physics, then we need to know why we do that. So this would be a goal, for example, for us. We can now shut down this screen, then you don't need to turn your head, and we are working up here. So the next generation observatories, there's two, like Einstein telescope is the European one. For the Americans, that's Cosmic Observer. So NV, next generation observatories. Would be, on the one hand, Einstein telescope. And if you want to look this up, the another project would be Cosmic Observer, Cosmic Explorer, sorry. Cosmic And what we saw on the picture is that we can see much further back, but this of course comes with a price. The noise ratio, so the precision, and I want to put this here, so the noise, the LIGO is something, and this, for those who understand this or like have some feeling for what this means, this is a frequency of 10 to the minus 3 hertz here that we have, seconds. And then in the next generation, we would have actually 10 to the minus 24, so one order of magnitude more, but this one order of magnitude will actually pose quite some challenges. So let's see what kind of challenges this takes. But first, the key takeaway here is that the interaction between black holes, as we saw that in the simulation, provides, on the one hand, a unique opportunity to explore novel physics, but then on the other hand, also, of course, for those who know about physics, it is also an opportunity to verify from a new perspective existing principles, and that of course means GR, general relativity. And that's then the starting point for the next section. This would be the modeling. We have done the observation and we need to do the modeling. So this is the physics side. The classical approach to gravitation, like if you took any class in physics, probably you are aware of gravitation as such, and then the predominant theory to do that, one of the best tested theories at all, is general relativity. And general relativity, if you do it for these kinds of projects, is essentially a PDE, a partial differential equation that you need to solve. So just to give those who have seen this already, you have the Einstein tensor. This is usually two components here, and then you have the cosmological constants. This is something that also is somewhat famous because Einstein first thought it was there, then he thought it wasn't there, then he thought it was there. It's probably there. And then we have here, this is the Einstein gravitational constant and the stress energy tensor. So what we see here, this typical thing that in popular science is known that space-time as such is curved. This is a metric here. This G, if you have ever had a course on Riemannian geometry, this would be a metric. And it, on the physics side, corresponds to the fact that the curvature of space-time has some impact. And then this here also contains the metric term. I won't go into the detail, but the Einstein gravitational tensor here. And this also contains this curvature of the space, matching this popular image of curved space according to gravitation. And this is more or less all the rest. So this is like the forces that actually attract each other. So in this equation, the point for us is this yields a PDE. Now the point for us here is, we could take on face value that this is just difficult, because it is extremely difficult in fact. So as the simulation that we saw before is in itself quite an achievement. But the problem with these PDEs is, because we have singular black holes, here singularities are unavoidable. And if you have ever thought about numerics or so, then you will know that singularities typically make things difficult. And here we have them intrinsic in the problem formulation. So that means bumping precision by just one order of magnitude is actually quite a challenge. So these things before have been computed on supercomputers. The next generation will also be done on supercomputers. It's not undoable. It's definitely something that the field can do, but it becomes more and more challenging. For this reason, and also from the perspective that for mathematicians needs some discussion. In mathematics, normally when we have a theorem, we might want to give another proof because we like a different style of mathematics or we want a different perspective on the proofs. In physics, that's a bit different. We don't have axioms. So having a different way of modeling a system is of intrinsic value because it allows us to reconfirm the observations in the model that we created for that from this additional perspective, giving basically much more value to cross-checks. So what can we do instead of GR? And that's actually not so easy, but it has been done over the last few years. There has been quite some work on alternative modeling. So instead of GR, which I want to here abbreviate as GR indeed, I want to use Feynman diagrams. And for this, we need to actually just get an idea of what Feynman diagrams are good for. So we want to talk about field theories. The idea of field theories, you will know this if you have any physics background, you will normally know this from the quantum world. Field theory are a very typical instrument to compute quantum mechanics. And here we want to use it to model, so to speak, the opposite end of physics. But the idea of quantum physics is that we write up or draw, in fact, we will possible interactions between particles, and then assign a probability. And I perhaps want to say probability expansion here. We have to clarify these two things. First of all, there is no particle, we have black holes, so this definitely needs some clarification. And then, of course, what kind of probability is that? This eventually will actually lead us to the mathematical framework. So this will be, in the end, the upshot of this section where we have those probabilities. We want to detect their shape and then try from a mathematical perspective to abstract them further in such a way that we then can take a purely mathematical perspective and don't need to think about physics anymore. The truth is, from a mathematical perspective, these theories are not quite well defined. So at the moment, for example, some of those expansions are not known to converge. It's actually an important problem, but that's a problem for physics. We accept that. We are not going to think too much about that. The physicists produce a theory that actually works pretty well in observation, so that's good. And of course, it is an important problem also to think about this well-definedness, but that's not what we are going to do today. We instead take those terms which we know contribute in a meaningful way, and we want to analyze them. But let's first see what particles are. So from the distance, and this is the importance, black holes are particles. This is actually the key idea here. So when we have those two black holes that we saw on the screen, that from the very far perspective, we can simply model them as two particles, and then we now need to think in what way will they interact. This is now the key point, and in fact, the difficult part. So normally, field theories use exchange particles, and in gravitation, we don't have such a particle at the moment. There's a hypothetical particle that will thusly do that. This is the graviton. It has quite exotic properties. So for those who know what that means, it's a spin 2 particle. I have no opinion myself whether it exists or not because I'm not a physicist, but that's what you need for this modeling. So let's keep that in mind and assume simply that we have a graviton. As mathematicians, we have no problems assuming things. And then our idea will be to draw these interaction lines. So for example, we have here a black hole. It would go in this direction. And we have another black hole. It goes in this direction with certain momenta. And then we normally draw some line. This would be one graviton, for example. And then we can, for example, say that there's another line. So these here would be gravitons. And then these would be black holes. We will later organize all those diagrams according to specific schemes, because these particles are actually black holes. We will also introduce an extra rule, and this is really necessary here and important, that these lines should not cross. That's why I simply drew them as parallel. But to give it more of an anchor for those who have a physical background, actually I don't want to give the amplitudes for this one. I rather want to give the amplitudes for a very classical theory, a muon electron scattering process. So there you can look these things up if you like. For even on Wikipedia you find exactly those formulas, or almost exactly those. So we want to get an electron. In the standard model there's antiparticles, so this would be a positron. It's not super important to have this, but what we need is here the momentum, P3 and P1. So we have one particle that comes in. There will be something happening to it. We need to continue with that. But it comes in with some speed. So particle speed. And then eventually something else, a positron in this case, comes out also with some speed. We keep this with certain variables. Typically these are 3 vectors because, well, we are in 3-dimensional space, if you don't believe in string theory. So then there's something in between. This is a photon. So, for example, this could be simply that an electron, you can normally read these also just from the top to bottom, that's totally legitimate. You could think, for example, that an electron and a positron come together and annihilate each other. Then you get energy out of this, a photon here in this case. This has a momentum, let's call it Q. And then from this, for example, you would have a muon. This is another particle, an elementary particle that is not super well known, but we can simply assume that it exists. It's pretty likely that it does indeed exist. The experimental evidence for that is overwhelming. And then here we get a positive charge on the antiparticle. So this is simply it's actually one of the easiest processes from so-called QED. This is quantum electrodynamics. One of the most important field theories, like one of the more basic ones. And here you, for example, would study this kind of diagram. So we have done the interaction, the modeling of the interaction. This is one of them. Here you would have, for example, another one where you have a more complex interaction. Something like that can also happen here. Like you could have further electrons, or you could have further scattering. There's many possibilities. We don't want to exaggerate, but we rather want to go to the second step, because we in the end want to go to mathematics. We need to write down some probability. Actually, this is a nice thing about this model. In the end, as a mathematician, you can think of this as writing down all the components in a probability space where the variables are independent, and then you project down to a conditioned expectation. And that means you write down a product of like basic probabilities, and then you integrate out. And that's exactly what we are going to do. I write this down in physics equations. This is actually the correct term, except that I won't write it up completely. So it comes with all the shenanigans of physics notation. Bear with me. It's a dimension, it's an integral over here, this internal momentum. This is called an off-shell momentum. Then inside we have certain so-called Pauli matrices. There's a way to deduce them from a more general theory. And then this depends on the momentum, in this case of P3. As a superscript, we have a certain other additional state, a spin in this case. And then here we would have a metric. We are not at the metric. This is a coupling constant for the electron, and here for the muon. Then we have another Pauli matrix. This is S1, yes, exactly. And then, not P1. And then this is one factor. This basically accounts for the probability of this part of the diagram. So normally we write factors that come, these are matrices, and we basically take their cross product here. And these normally are assigned to all those edges here that interact. So the idea is kind of a localization of the probabilities here. And then we would here have a metric tensor also, G mu nu divided by, well, the internal momentum here. That's the momentum here. It comes, so to speak, alone in this case, and then we actually would repeat this term only for the bottom part with corresponding Pauli matrices. And then, in addition, we need to do momentum preservation. This is actually, so far you would think, okay, I mean, that's a product. Probably you can evaluate this integral over q, because this doesn't depend on q. And then you do integrate q square. That's something that we can actually do. However, there's something called momentum preservation. So in each of the vertices here, we need to make sure that the momenta add up to 1, add up to 0, and that means that these terms effectively depend on q. This is like one of the challenges as a mathematician reading these things, because this is not how we would normally write it. But I want to just explain this to you in the way that physicists do that, because it's like really an important skill, I think, to be at least able to roughly read this type of literature. So we have here simply a delta function. You can see this plug in for P, or for Q, plug in P1 and P3, but of course you need to also then adjust the integration variable, and the same thing for the other vertex. This is P2 minus P4, and then plus Q, because it's the other direction. You always need to take care of the direction of the arrows. So this is an integral, and that's in fact almost everything that I wanted to say, except that there's of course many of those. So in fact, this is something that if you don't come from the theories, hard to believe initially. There's billions literally of those diagrams. And if you want to compute the theory eventually, if you want to make predictions about how black holes actually interact with each other, you really need to compute every of those integrals, every of these billion integrals. How do we organize them? So this kind of diagrams are pretty typical. This is called tree level. You can think of this as it's a kind of a tree. If you take one direction, the important point, it has no loops. This would be a one loop. It has one loop here in the diagram. And then if you do that, you can of course add further things. For example, let's say we have further gravitational interaction. Then here we have two loops, and so on. And normally you have a loop expansion. So you have this tree level, which is exemplified by this integral and by this diagram, then one loop, and two loop, and so on, times t. This t is normally a coupling constant. Depending on the theory, it depends on string theory, so it's string coupling constant, and quantum field theory can be essentially Planck. So these things depend a bit, but let's say plus t squared just to illustrate things. But of course, the question is, if you want to compute your theory to a specific precision, you need to actually evaluate more and more terms. So, and that will actually be an important point here. Namely, if you look at LIGO, so the gravitational observatory that we actually have and where we do have measurements, we can do such modeling, and there's an implementation of this. With precision 10 to the, it's actually pretty impressive, 10,000. This is far beyond what we can measure. I mean, whether this is really correct, all 10,000 places, I mean, we will never know. But this in principle is the precision that we have in those individual terms. Doesn't mean that we have all the loop orders, that's not, and that will be a point, but at least the terms that we need to know here for this LIGO observations, we can compute to mind-staggering precision. This is an advantage over the PDE computations. We have access to almost arbitrary precision. That's good. For the next generation, however, so a next generation would need further loop orders. And I wrote this down, I think up to 7. We need, this is the prediction. Of course, one needs to cross-check these things, that's how things work in reality. But the prediction is that we need up to loop order 6. So many, many loops, and that will mean very complicated diagrams. The general idea is that the more loops you have, the more complicated your diagrams will be. So here the upshot is, if you want to model black holes using Feynman diagrams, then you need to evaluate Feynman integrals, this type of integrals, and it is essential to evaluate many of them, because we have literally billions of them, and to evaluate them to high precision. It doesn't need to be to this high precision, but we do need high precision anyway. Okay, so then we can move to mathematics. I hope you feel good about that, because now we are, for those who are mathematicians, we are going to do things that you have seen already. Let's see. Oopsie. Oh, I leave it there. It's okay. So in the mathematical framework, we need to ask ourselves, if we have such integrals, what's the common feature of these integrals, and how can we classify their difficulty? From the physics perspective, for example, the loop order is a descriptor of how complicated those integrals are. From a mathematical point, we ideally match this. We want to have some understanding how complicated such an integral is, and then, of course, step by step, by increasing difficulty, find a way to evaluate them. So the first step is, and I will skip this, there's a way, essentially through differential recursions, to reduce these many billion integrals to very few. And this is an ongoing topic of also mathematical research. Very interesting, but it's not the topic for today. So this leads then to D modules, if you ever want to know this name. But what I want to really do is, let's just assume we have simple integrals. And by simple, I could mean, for example, the arc cosine of S. This is the integral from 0 to S, and then dt square root 1 minus t squared. I hope this is something that many of us have already seen. And as you see on the left-hand side, this is an integral that we can truly evaluate. On the right-hand side, this could be, for example, one of the terms, and it actually is, one of the terms that might occur in some of the tree-level amplitudes. I have just given you an expression that allows you to not only very efficiently compute that, but you also, this is not so obvious, it's actually easily possible to detect certain, how would I say, to detect certain redundancies in this type of integral. So if you have similar integrals from calculus, you might have seen certain variable transformation that always leads to this arc sine or arc cosine and so on. So this is some good case. This is a classical one. But if we go back 150 years ago, where not this kind of Feynman integrals, but just Lagrangian formalism was the topic, then we already saw the following type of integral. This is an elliptic integral of first type, or first kind one says. And there we have the integral of dt, 1 minus t squared, 1 minus kt squared, and then square root of this. And perhaps you want to restrict here k between 0 and 1. Of course, perhaps one wants to exclude the k is equal 0, because that will, as you see here, if this is k equals 0, you recover this case, but we can include it for now. So it is something like the improper case. So what's the key message here? The key message is that if we add only one factor, the problem suddenly becomes from relatively doable and classical in the true sense to almost impossible. So even giving some special values of these elliptic functions is not super easy. We have one, so k of 0. We can match this with this integral, then this factor collapses to 1. So we simply have arc sine of 1. And this is something that we can indeed compute exactly. For example, this, just to give you a feeling for what you would expect, there's the following special value. This is one of the simpler ones that one can find. It's at an obscure value, square root 2 minus 1. I mean, why not? It's gamma 1 over 8, gamma 3 over 8, square root 2 plus 1, and then 8 times fourth root of 2, square root 4, square root pi. So this is not exactly a pleasant value, and it's still one of the more pleasant values that you could get out of this function. For most values of k, it's just not possible to get a closed form for that. If we connect this back to our original question, and this is the theme of this talk, we need to ask ourselves, what does this mean for the physicists? This means that we need to numerically evaluate this integral. So we now have two tasks. How can we evaluate such integrals in the most efficient way? This will be one thing. This will eventually lead us to modular forms. But then also, how can we understand how complicated these integrals are? Like in the end, these modular forms will not come out of the blue sky, but we need to say something about why this integral would exactly lead, for example, in this case, to elliptic modular forms. So let's try to answer this question. And for this, we look at the denominator. This is a square root, right? Of an order 4 polynomial, you can take this actually as a definition of the elliptic function. So if you have a polynomial of degree 3 or 4, and then a square root out of this, this is an elliptic integral. That's a classical definition. And if you then perhaps have ever heard of elliptic curves, for example, and that's the same, literally the same name, this is where the connection comes from, an elliptic curve would be also arising from such a square root. So what we do here is the denominator, this corresponds to a double cover of, well, let's state it easy first, of C, which contains T. So we have here this parameter T, and to each choice of T now, we allow ourselves to choose one of two values, namely the two possible square roots of this polynomial. And that gives us a double cover, so we have our line, and then on top of this line, something like this. So this would be a typical geometry for such an object. So here, actually I shouldn't write C, I'm jumping ahead. This a priori, this is R. We absolutely want this to be R, sorry. So we have such an object. This object turns out to be a double cover, it turns out to be an elliptic curve. All those elliptic curves can be written in terms of those polynomials, and this is a very classical theory again, like going back to the previous century, and nowadays studied very well, and that explains why we can evaluate such functions. We have such double covers. We will introduce in a second some kind of theory for how we study these things. And then eventually the geometry of whatever occurs here in the denominator, for example, would determine the level of complexity to evaluate those integrals. Let's try to make this more precise. What we will be handling is so-called period integrals. So for studying period integrals, we first need an affine real variety, affine real variety is the zero set, and here I mean the joint zero set, of a finite number of polynomials infinitely many variables in. Let's say x1 up to xn. So we just take some variables, we take some polynomials, and then we take their series set. What would be the most fitting example in this case? Well, we have this variable t. For example, we instead of x1, of course, we can rename it. Let's rename it to t, and let's say y. We take y squared equals 1 minus t squared, 1 minus k t squared. Right? Because the pair of such points, y and t, that satisfy this equation would be somehow modeling this denominator. And the key idea here is then, if I have this object, basically this set, these types of integrals can be intrinsically formulated on them. Namely, I need to find out how do I formulate these boundary conditions. Now this is like harmless, right? I mean 0 to 1, I mean what should it be? Like this means, of course here, let me first write it up, a semi-algebraic set. And we have the example here that 0 less equal t less equals 1. It's very hard from this example to guess what the right notion is, but actually it turns out the right notion is we just take some variable here, for example those, and we want them to be bounded by, well, polynomials again. Just the same type of objects that we use to define our variable, our object here, the variety, we also now use to determine the boundaries. But instead of equalities, we allow ourselves inequalities. This then allows us to, in turn, formulate whole integrals. So, semi-algebraic sets, inequalities for continuing the notation here in terms of polynomials. And with this, we can actually say what a period is. So a period, in this case, and I want to write, because this is not quite the general definition, I will write an affine period. The integral of a differential form on a real affine variety along a semi-algebraic set. And now we have the first anchor to determine the complexity of those things. If anything, then most likely those varieties, the more complicated they are, the more complicated it will also be to determine those periods. And that roughly is actually true. There's quite some depth into this thing, and the truth is we don't know even close to as much about this as we would like to know. But the rule of thumb is the more complicated the variety is here, the more complicated the associated periods are. And so now we explain also from a geometric perspective, this corresponds to a so-called rational curve. Which essentially means you can visualize it as a line. This is, like from a geometric perspective, this is more or less a line. While this here, I was already hinting to that, this corresponds to an elliptic curve. Oops. And elliptic curves are strictly more complicated than rational curves, and hence this integral is strictly easier to calculate than this one. These types of integrals are the only ones that we have true hope to evaluate in closed forms, and for all the other ones we need to find more elaborate techniques. So let me give you quickly some example of such functions that you might have known. So if you, for example, have taken some number theory courses, well, I'm a number theorist, so I like these examples, then you know theta, the Riemann theta function. It's anyway a rather famous function because it's connected to some of the Millennium problems, and you can say a lot about those things. One thing that you can ask yourself is, what's the value of the theta function? So the theta function would be as such, the sum from n equals 1 to infinity, n to the minus 1. And then you can ask yourself, what is theta 3? This is actually not so easy to answer, but we can write it in terms of a period, which indeed facilitates the study of these values. So we have x, y, z, and then we have dx, dy, dz, 1 minus x, y. So this is one valid expression for this theta value, and so we have connected some of the things that you have already perhaps seen in a different context to period integrals. This is not a coincidence. There's many examples of these things. They in general are examples of so-called iterated integrals, which are a bit of a special case here, but it turns out this special case, thanks to these differential recursion techniques, is actually one of the important special cases for the purpose of physicists. So iterated integrals, just as an example, would be here then, that you say the dilogarithm or polylogarithm at z is minus the natural logarithm of 1 minus z. You can write this as the integral from 0 to z dt 1 minus t. And then you iterate that by saying that the polylogarithm n plus 1 of z is simply the integral of from 0 to z of the Li n t divided by t dt. So you can plug these things in again and again, and then you see that you here have more and more t's in the denominator, and the fact that this goes from 0 to z, but the integration variable t here becomes a boundary point, in the end means that you have this type of boundary conditions, which is a semi-algebraic set on a variety, in this case a rational variety. This is only polynomials, 1 over t and so on, p. So we are actually here on a Pn, or P1 even, and that is a variety. Turns out to be an affine variety, although we typically want to go to the set of compact varieties, but for our purpose we can easily think of it in terms of affine varieties, and that means these things are examples of period, and they are called iterated integrals. Well, I think that's obvious why. So this is the pattern, and this is the type of objects that we would like to understand better in the context of physics. So there's quite some work on these, like there, for example, was breakthrough work on this type of integrals here, on this type of integrals here by Francis Brown. Then, like just 1.5 weeks ago, there was a European grant with 10 million euro, which is quite a lot of money, to understand the things that come beyond this. So the things that come, for example, with elliptic curves. This is a rational curve, then the elliptic curve would be the next step, and in fact beyond. And the beyond is what we want to go to next. You still need to do a concrete mathematical problem or contribution, because at the moment I've done the framework, but I want to get you to at least some concrete mathematical contribution, and I'm only going to sketch that, as you can guess. So the point here is that we need to evaluate many of those integrals, and we need to be able to compute those forms in a way that allows us to detect redundancy. The way you do this is through a connection to modular forms. And the key point here is the so-called modular parameterization. From the perspective of our problem, this amounts to having convenient, in fact more than convenient, excellent, in fact, coordinates for evaluating those integrals. So the point of this is excellent coordinates to evaluate, let's say, iterated integrals. The modularization and modular parameterization is not the keyword that most people know this type of results, but they are famous. So modular parameterization is one part of what Weiss proved, and what earned him the Fields Medal, or well, didn't earn him the Fields Medal, in fact, which in the popular literature and canon is normally associated with the Fermat's last theorem. So Weiss proved that Fermat's last theorem actually is true by proving that elliptic curve, so the object that we have seen already in the denominator of our integrals, that those elliptic curves are modular. And his proof, among other things, also provides a modular parameterization, and that means that his proof, among other things, says that we can use these modular forms as coordinates, as very convenient coordinates, to compute those integrals. So an elliptic modular form would live on the upper half space, where you take the imaginary part of tau greater than 0, and then you want to take a function from h to c such that a tau plus b divided by c plus tau plus t is c tau plus d to the k f tau for all. Well, we can here be generous. This is not exactly the case that is relevant, but just to get an impression, A, B, C, D in SL2Z, and then plus some other, plus extra condition that I don't want to talk about. The modularization, the modular parameterization basically tells us specific F, and we can actually describe which one, there's ways to determine those, yield or correspond to the coordinate t in y squared equals 1 minus t squared, 1 minus k t squared, the thing that we have seen before. This was one variety, and if we find a specific f that would be one of those t's, then we can actually use that to get further coordinates. Namely, this f depends on tau. And one property of tau, key, is f of tau is like some constant, let's say C0, C1 exponential 2 pi I tau plus C2 tau, 2 tau, and so on. In this case, I just write down. So the point is we have a Fourier expansion. Fourier expansions are extremely well behaved when it comes to numerical integration. In particular, if this constant is not there, which for those forms is actually the case. And then you can use this to indeed achieve this 10 to the minus 10,000 precision. This is where this comes from this type of argument. So let's see what we can do beyond this. So elliptic curves are established. I mean, these things were proved in 95, and of course, this is only the fact that this was used in numerics is only a very recent development. But mathematics has of course gone on. So the next case here is paramodular forms. Why is that we need to argue this? The reason for this is that we have a conjectural modular parameterization. So the modular parameterization is now for so-called Calabi-Yaus, by golly, Jeff, modular parameterization for Calabi-Yaus, Calabi-Yau threefolds. You can think of those objects as the ones that are just so complicated that we can still hope to do something, but it's the hardest of all the possible cases. If you're a tiny bit more complicated than that, it's hopeless. If you're easier than that, you suddenly have a plethora of more tools, and this is just this edge case that escapes us. And for some conspirational theory reasons, this is the case that typically appears in physics. So it's quite useful to have a modular parameterization, so we want to at least quickly understand what paramodular forms are. So the generalization here is that we instead work on this case, the upper half space. This is the space of 2 times 2 matrix, which are symmetric over C, such that the imaginary part of tau is positive definite. This is now a symmetric matrix, so it makes sense to ask that it's positive definite as a quadratic form. And we have an action which is very similar to this. Here, this SL2Z actually was acting in the background, even though I didn't specify it. And we just need to rewrite this in such a way that it still makes sense for matrices. So we have A tau plus B, C tau plus D to the minus 1. And then this would be the determinant, because this C is now a matrix, the tau also, to the K, and then F tau. And then 4. Well, A, B, C, D should be in the paramodular group and this is the matrices. You can write this as matrices in the symplectic group of size 4 times 4. And here you would have a set 1 over set divided by n set, n set, n set, n set, n set, and then set here, that's all. So the point being that you have some divisibility properties. The rest of the entries are just demanded to be integers here. But you allow for one entry that is actually a fraction entry. This is some group that, well, of course, one needs to verify that it is a group, and it turns out to be a very useful one. So you have a whole family for so-called level n. So this is also said. So n is here the level. And then Golitchev believes, and in fact many other people also believe, that there's a modular parametrization for these paramodular groups. This has only in summer been cohomologically verified, so this becomes more and more likely, but we still are very, very far from a proof. But for the physicists, that's totally okay. I mean, if we really want to serve physics here, it's okay to occasionally draw from a conjecture, even if we are only, if we are still very far from actually proving it. So let's work with this. And then what we want to do is compute these forms, because I was saying that elliptic modular forms are accessible, and there's a long tradition of computing those things. So let's actually see how we compute them. So f of tau can be written as an expansion, and here I want to be brief. So tau 1 said, I write em tau 2, so here tau has a decomposition. We decompose the form according to a plot decomposition of this. We write e of tau as exponential 2 pi I tau. This is a standard notation from modular forms. And the point is that this is connected to elliptic modular forms. In other words, we can compute it. We are trying to set up something recursive here. We have a decomposition of these paramodular forms, and I made a mistake here. This should be an n here, and this should also be an n, but otherwise it's correct. We have a decomposition in objects that we already know how to compute. And then in addition, we also have f of tau, a Fourier expansion. We can actually say T in specific matrices, 2 times 2, symmetric with entries in set, and then one needs to do a specific thing with off-diagonal entries. The point is that we have here numbers, and then E of the trace of T tau. So this is a Fourier expansion, and this one is symmetric with respect to a group, subgroup of GL2 set. And then the theorem, this is actually a rather recent one, building up on earlier work, but we finally managed to extend this also to this paramodular case. So this is a theorem, in this case by Jan Bruinier and myself. Myself, this was 2024. And what we showed is a simultaneous expansion formal expansion with these symmetries. So these symmetries here, and you can of course take generators of this. There's only finitely many generators of these subgroups then. Simultaneous formal expansion with these symmetries converges automatically, and is the paramodular form. One needs to add some things. We didn't write this up in that paper, but one needs to add some classical stuff about vanishing orders of single modular forms. But what we get from this is actually a formally proved way of computing paramodular forms, which is quite good, because before we were often using ad hoc methods, and this is a way of computing this that always works. I should say there's a conjecture that says that only one specific symmetry suffices here, and unfortunately we're not able to prove that one, although it's probably, well, I mean, it's hard to say whether it's correct, but we were hoping to be able to prove it. We were not able at the moment, but at least this is a formal algorithm to compute paramodular forms, and then we close the circle, because now we have some extra contribution for how to evaluate those integrals that indeed, those things indeed occur in the computation of black holes. And then with that, I want to finish. Thank you.
So Martin?
Can you say something about the formula for k of root 2 minus 1, like when it was proven and how? Probably
This specific formula that I gave, this honestly I don't know precisely, but I would think you just specialize you write this as a special value of a hypergeometric function, and then use the evaluations due to Gauss. That's that's what I would guess how you can prove that, but I don't know it from my top of that.
So you mentioned this potential modularity for Clapeyron threefolds. Have you looked at the modularity results for abelian surfaces and potentially evaluating these integrals for maybe sort of hyperelliptic curves?
So this would be, from a mathematical point of view, that would be interesting. I haven't really looked at this. The problem is that those don't seem to appear in the gravitational computation. But yeah, I mean, of course one can try, because there we have modularity theorems, and one can try to use those computations. But however, this will be tough, because there normally you need to compute Bianchi modular forms.
Yeah.
So there but it's a super interesting question, of course, yes, from a mathematical point of view.
You and Jan had a similar result for modular forms, which relate to the Kudla conjecture.
Yes,
right?
exactly.
So is there conjecture in the background too? This is
So this was an attempt to set up a completely geometric way. I mean, our original proof for the Kudla conjecture, I mean, this was one of the key, well, the key result in the background of my proof is Jan of the Kudla conjecture, and that was a somewhat algebraic, somewhat analytic proof. And our desire was to give a purely formal algebraic proof, so formal geometry as a tool which we can, first of all, specialize mod P, but also that would circumvent some of the systematic problems with our previous proof, which hinders us from proving the unitary Kudla conjecture. And so this was our first attempt of setting up a framework that would work in this setting. Unfortunately, the criterion that one uses here, this has to do with formal geometry, are not powerful enough at the moment to prove the unitary Kudla conjecture, but at least it gives us some understanding of these important cases and of how to set up this formal geometric framework. That was the background here.
Any other questions? Let's take Martin again.